start off by briefly going over some basics of cavitation erosion. I'll spend the bulk of the time, unintended, on the modeling of the bulk fluids. Next, I'll go to cavitation erosion modeling, and lastly, I'll finish up with a discussion and conclusion. So, bubble nuclei are present in all liquids in the order of millions per meter cubed, and as they experience pressure changes, they might collapse near a wall, which might result in surface erosion. If we look at experimental and numerical data, we can see that the magnitude of surface erosion depends on 4 factors. These are the number of bubble collapses, the bubble collapse drying pressure, bubble diameter, and bubble distance to the surface. I'm mostly interested in non-symmetric bubble collapses as shown in the video above. So you'll see a collapse of a bubble, you see the microjet and kind of the collapse of a toroidal ring now. And these two pressures superimpose, and depending on the distance, as seen on the bottom left, I don't know if you can see my mouse, but hopefully you can. As seen on the bottom left, you can see different damage patterns depending on the distance of the bubble from the wall. The main difficulty with computational cavitation erosion is there are thousands of collapse events per second, and there's a wide range of temporal and spatial scales. The temporal scales go from milliseconds from bubble collapses to minutes, hours, days for cavitation erosion, and the spatial scale goes from micrometers to millimeters for bubble diameters and centimeters to meters for engineering devices. So the problem needs to be separated into kind of 2 stages. The first one is the bulk flow model, which should provide the 4 factors I spoke about previously, and the bubble collapse models, which should take those 4 factors and give us the volume, mass loss, or erosion coefficient. So let's start with the bulk fluid model. Ideally, we would use Euler-Lagrange, but it is prohibitively expensive. Hybrid Euler-Lagrange is a nice idea, and there has been some work done, but again, it's a bit too expensive. And what we're left with is Euler. Previous work has been focused on multidispersed description, but in this work, a polydispersed description is used, more specifically a multifluid model. This is a set of conditioned volume average governing equations, the continuity equation, the conservation of mass and linear momentum. And to close the set of equations, you need to model 4 terms. These are the mass exchange terms in a second equation, and the Reynolds stresses and momentum, interfacial momentum exchange in the third equation. So starting out with momentum transfer, I only consider the transfer of momentum between the bubbly phase and a continuous phase. 5 forces of model. These are drag, virtual mass, lift, turbulent dissipation, and wall lubrication, and these are their forms. And each of these forces needs to have a coefficient in front of them, which is kind of the tricky part. A Boussinesq eddy viscosity assumption is used, and the K epsilon turbulence model has an additional 2 sources which describe kind of the induced turbulence of bubbles. Lastly, mass transfer is modeled both continuous terms such as cavitation and isothermal expansion, and discontinuous terms such as breakup and coalescence. Discontinuous terms are modeled using a fixed bit method called Krishna, which has been validated. At the top right, you can see an analytical validation for pure breakup. Again, we start with the black line here. Analytical results are the lines, and numerical results are the dots. So we start with the line here, and we end up with breakup here. The same thing is done for coalescence. We start with the black line here and end up with the blue line here. The most challenging part has been validation, because there is strong coupling between the interface forces, bubble disturbance, and bubble breakup and coalescence, as seen at the figure on the right. And the idea behind the validation is to separate it into 3 stages. Firstly, to validate interfacial forces on mostly non-dispersed low phase fraction cases. Next, model bubble-induced turbulence with similar cases, but with a bit more bubbles, a bit more turbulence. And lastly, kind of model mass transfer and fully polydispersed cases. And to do this, you need a good experimental database, and that is OFW. So this is a set of experiments in a 200 millimeter diameter vertical pipe, which is about 7.8 meters high. You get 18 measurement planes per experiment, and this is what the setup looks like. So at the top in the red, you have the measurement plane, and you inject bubbles at different heights. Numerically, it's a bit opposite. So you inject bubbles at the lowest plane, and then you have different measurement planes across the height. What is exactly measured is bubble velocity, bubble radial distribution per bubble size with a resolution of 0.25 millimeters, and the bubble size distribution. And 3 cases have been identified for the first phase, so the validation of interfacial forces. These are measuring points 19, 30, and 41. And I'd like to present some results for measurement point 19. So this is what you get in the paper. At the bottom left, you have the distribution of bubble sizes across the heights. So you can see that the bubble mostly stay more dispersed. At the bottom right, you can see the velocities. And at the top right, you can see the integral phase fraction of all of the bubbles. And you can see that the bubbles start in the black line next to the wall. And as they go across the height, they stay next to the wall with a bit of dissipation. So this was for a case of where the injectors were 1 millimeter in diameter. And this is the exact same case, but the injectors are 4 millimeters in diameter. So similarly, the distribution is on the larger size. So the average bubble size is larger, but more dispersed. However, you can see that the bubbles start near the wall, but they tend towards the center. So different behavior being wall feature centipede is exclusively due to the difference in the bubble size. So to validate this, I used the set of equations shown before with these coefficients. Again, noting that no continuous or discontinuous mass transfer is modeled, so no isothermal expansion and no breakup and coalescence. The models were used for virtual mass 0.5, drag was solid beam light off from 2020, turbine dissipation with Burns, lift was custom shown on the next slide with wall treatment of Shale and Podolsky, and wall lubrication and W turbulence for MIT models from Wilczek and McCollum. And this is the lift model used. So again, in red, you can see some red and green, you can see some popular models from Hessenketter and Tomiyama with different aspect ratio models. Next few lines are experimental results, and the black line here is the implemented lift coefficient. Again, this is for water air mixture at a bit higher pressure than usual. And you can see that the inversion is around 3.8 millimeters. Okay, so now I'll present some results. So starting with the case of a 4 millimeter nozzle, this is the inlet distribution, discretized into 1, 2, 3, 4, 5, 6 bubble classes, with the average bubble diameter being 5 millimeters. And this is the distribution across the height. So we start with an average distribution of 5 millimeters and end up with smaller bubbles, so more breakup than coalescence. And I'll take a minute to explain this slide because there's going to be a lot of similar ones. So this is the phase fraction of bubbles of 2.5 millimeter size, meaning bubbles, all of the bubbles between 2 millimeters and 3 millimeters. On the x-axis, you can see the pipe radius with the wall being on the rightmost position. Lines are experimental results, again, separate from convection. Dots are numerical results, and they're colored in different heights, with red being the lowest measurement point and blue being the highest measurement point. So the bubble starts near the wall and they end up near the wall with a bit more dissipation. And you can see good-ish agreement between experimental results and numerical results. This is a larger bubble size, so 3.5 millimeters. Again, good prediction of where the bubbles are. The integrals are different, the height of the lines, but this is due to not modeling breakup and coalescence. We can see that there is more breakup and coalescence, so more bubbles are entering this class as height goes on. Next, 4.5 millimeter bubbles are kind of modeled excellently. So we start with red, orange, yellow, blue, light blue, blue, and dark blue. So excellent agreement for 4.5 millimeter bubbles. Similar for 5.5 and 6.5, again, noting that the integrals are different because there is more breakup than coalescence. Next, we do the same exact thing, but for a 1 millimeter nozzle, discretized into 5 classes in this case, with a smaller average size of 3.5 millimeters. It stays mostly non-dispersed, so more bits, more coalescence and breakup. And again, decent-ish results, not integral-wise, for small bubbles of 1.5, 2.5, 3.5 millimeters, and difficulty start with larger bubbles, which usually tend towards the center. So numerical results show that bubbles should travel towards the center, but experimental results show that most of the bubbles stay near the wall. And the same is true for bubbles of 5.5 millimeters. So this is due to wall-induced lift, which is a term used to describe the complex interaction of vortexes and gap effects as the bubble approaches the wall. And it's significant for a dimensional distance of less than 2. There's been several papers on this, but I'd like to highlight Shi et al. From 2020, which says that the total lift can be considered as a sum of linear shear lift, wall-induced lift, and a delta, which is less than 5%. And the expression for wall-induced lift is shown here. I also like to highlight the leading term is to the -4, so meaning that the expression is sensitive to the wall distance. And because of wall-induced lift, we get this graph here with the red line showing kind of the difference for the same bubble, whether it goes towards the center with empty dots or towards the wall with full dots, depending on the wall distance. So lift is in fact, so the final position of a bubble is not only a function of the bubble size, but the bubble distance from the wall. And this sort of implemented wall treatment is also implemented, where the bubble wall distance is calculated as the average of all possible positions. Shear and Podolsky treatment is used on the wall, and for this set of equations, linear shear has been disabled for dimensional distances less than 4, which is not ideal, but I want to just highlight some results and ideas. So again, same set of results as in the previous slide, and the differences are apparent as we get to the higher classes. So previously we saw kind of the blue line being here, so fully center peak, but here we are able to capture a bit of the wall entrapment for 4.5 millimeter bubbles and 5.5 millimeter bubbles. And I'll assume that your bulk fluid model does all of this. You need to capture cavitation erosion. Two ideas behind this. The first set is probabilistic models, where you take all of your phases of interest, you build a hemisphere of cells around them, and you expect them, and you examine them in each time step for 2 criteria. The first one is vapor, where if there are bubbles or not, and the second one is if there are bubbles and they collapse, can they do damage? And there are 2 common criterions, microdrift and bubble collapse models. This is validated against experimental results in a kind of monodispersed consideration. So again, you have a pipe going on a plate, and you will get some cavitation erosion on the plate. This is a movie of the actual experiment. So again, you can see the cavitation sheet forming. Red lights indicate where we expect cavitation erosion, and the coloring at the bottom is the erosion coefficient. This is a comparison between experimental results, here shown in red, and numerical results of 2 different models. So again, a bubble collapse model and a microdrift model. They both show excellent agreement, and this is the evolution of both of these models as time goes on. Another option is not to use probabilistic models, but to actually model a collapse of a bubble. You solve Euler equations for this in the conservative form, level sets to track the interface. A multi-handle scheme is used here, and jump conditions are implemented using the real Gauss methods. And it has been validated quantitatively and qualitatively against these results. So this is the same result as shown in the figure here. This is a collapse of a helium bubble in air, I believe, or an air bubble in helium. Great. So let's give some conclusions. The first conclusion is the bulk fluid model works well for all individual bubble classes as long as they're far away from the wall. And the main difficulty with modeling wall-induced lift is the leading term. It is very sensitive to where the exact bubble is. So you'll get an order of difference if the bubble is 1.9 0.05 or 1.15 dimensional distance away from the wall. So this is something I'm very much working on, and hopefully I'll get something done soon. The cavitation erosion model works fine. So the probability model has a good correlation with experimental data. And the idea behind using a polydispersed description is to be able not to have a set hemisphere diameter, which are user inputs, but to have it variable depending on the bubble size, as we expect smaller bubbles to only cause damage if they're right next to the wall. And lastly, the idea, hopefully, is to use bubble collapse pressures, so the ones simulation that you've seen of bubble collapsing, kind of build a library and implement that instead of using a probability model, hopefully sometime in the future. That's it. I'd like to acknowledge Dr. Lucas, Dr. Hansch, and the group from HDDR for providing the helpful experimental data. And I'd like to thank my industrial sponsor, Atom Chemical, for their financial and technical support. That's it. If you have any questions, I am looking forward to them.